Hello, welcome to Discrete Maths 1081. This is Chapter 2, again some more number theory, and this is question 10e. And so we're asked here to solve a congruence equation. So we're looking at 111x, it's congruent to 75 mod 321. To put it into, well, complicated English, it says I'm trying to find an integer that when I multiply it by 111 and I divide the answer by 321, then the remainder is 75. Now, this equation may have no solution, or it may have lots of solutions. There may be only one solution, no solutions, or lots of solutions. And the way we check how many solutions there are is again using the GCD. So we're interested in calculating the GCD of these two numbers. And if that GCD is a factor of this number, then we have solutions. And in fact, that GCD tells me the number of solutions. If the greatest common divisor of these two numbers doesn't divide that one, then there are no solutions. So the GCD controls the number of solutions of the equation. Now you might be able to do it by inspection. In fact, I can see that 111, if you know your 37 times table, is 3 times 37, and this is obviously 107 times 3. So the GCD of these two is 3, and 3 divides 75. So I can see just from the numbers it should have solutions and should have 3 of them. But in order to find those solutions, I need to use Euclid's algorithm, and so that's where we begin. So we apply Euclid's algorithm. So even if you didn't know your 37 times table and you didn't see that was divisible by 3, then you can get this out by using Euclid's algorithm. So to use Euclid's algorithm, we simply take this number, we're going to divide it by 111, only goes twice, and I think you need 99 to make up the difference when you do the long division. So again, think about what the algorithm tells you. It says that the biggest number that goes into both of these two has to also divide this number. That means the GCD of 321 and 111 equals the GCD of 111 and 99. So you can repeat the process now. You can repeat the process on these two numbers. So that tells me 111, well that's 1 times 91 plus, 1 times 99 I should say, plus 12. And I use the same argument. The GCD of these two numbers is the same as the GCD of these two numbers. So repeat the argument, 99, number 99 is 8 12s are 96 plus 3. And finally, repeat the argument on these two, but then 12 is equal to 3 times 4 plus no remainder. So clearly the GCD of these two numbers is 3, which is the last non-zero remainder here. So there's the GCD, the last non-zero remainder. So at this stage, I'm going to say the GCD of 111 and 321 is equal to 3. 3 is a factor of 75. So conclusion, the equation has 3 solutions, mod 321. So the GCD tells me it's got solutions because it divides that number, and it tells me how many there are. GCD controls everything in the problem. Now, to find the solutions, we now backtrack through Euclid's algorithm. So I take the GCD and I'm going to write it as an integer linear combination of these two numbers that I started with. So that's 99 minus 8 times 12. And I'm going to cut a step here and say, look, 12 is the same as 111 minus 99. Now think of these as lots of. So this is one lot of 99 plus 8 lots of 99, which is 9 lots of 99 minus 8 lots of 111. 8 lots of 111. And again, you can check without checking all the details, you can check your answers looking fine by just looking at the last digit. So 9 9s are 81, that ends in 1, or if you will 11, minus 8, and 11 minus 8 is 3, so that's looking good. I can now replace the 99, so I've used that equation. I now replace the 99 using this equation, and I write this as 9 times 321 minus 2 lots of 111 minus 8 lots of 111, which is 9 lots of 321. I've got 9 2s are 18 lots of 111, minus 8 is minus 26 lots of 111. So 18 plus 8. So there's the Bezout identity. There is the Bezout identity. Now you compare back with what you had before. You want to change this 3 now into the 75. And so to do that, I'm going to multiply everything by 25. So I get 75 is 9 times 25 times 321 minus 26 times 25 times 111. If I now read that modulo 321, then that term disappears modulo 321, so I get minus 26 times 25 times 111 mod 321. And now I compare it back with the equation I started with. It says I want 111 times something has to give me 75 mod 321. Well, 111 times this number, so there is my x. There is my x. So the basic solution is x is congruent to. Now, this will give me a congruence mod 321, but to get my 3 solutions, I need to divide the modulus by 3. So I will get minus 26 times 25 modulo 321 divided by 3. Now this number here, so that's minus. This gives, if I halve that and double it, I get 650 here. Let me just check, I did the arithmetic before. Probably need a calculator at this point to help a little bit. Yep, so I get minus 650, which is congruent to minus 8 modulo 107. So the 3 solutions are x is congruent to minus 8, which I can do something with in a moment. To get the other solutions, I want to give the final answer back mod 321, so I'm going to keep adding on 107. So that would give me 99, and add on 107, I get 206 modulo 321. And if you wanted to, you could rewrite minus 8 if you wanted to as 313. Doesn't matter, or you could leave it as minus 8 mod 321. And there are the 3 solutions modulo the modulus you started with. So the tricky step is you've got to find your x using the Bezout identity. And remember that at the end you have to divide the GCD, so you have to divide the modulus, I should say, by the GCD to get you the new modulus. And once you've got that, you can use that to work your way back up to the 3 solutions mod 321.